guys, Mrs. Traver here. Today we're going to talk about area models, which is a way to do probability. So our learning target is to be able to do just that, and you'll know you'll be successful when you can find out how to use rows and columns based on probability and statistics. Let's jump in first with an algebra skill, which is multiplying binomials. We have the box method we can use for this as well as FOIL, but let's look at the box method for this one. In this situation, I would take 5v plus 4 and I put it on the side, and 3v minus 6 on the top. Each box is filled in by multiplying the row and column it came from. So 5v times 3v is 15v squared. 4 times 3v is 12v. 5v times negative 6 is negative 30v. And 4 times negative 6 is negative 24. We then can combine like terms here and get our final answer, 15v squared minus 18 v minus 24. The reason why this is called box method is because we make a box, and the reason why we're doing this now is because when we do area method, it is really the area. So like if this was a box that we were trying to find the area of, this would be its answer for area. Here example is one just like that. So here is a rectangle and we want to find the area of it. So I would do the same thing and set it up with 8x minus 4 and 5x plus 6 in the different sections. 8x times 5x is 40x squared. Negative 4 times 5 is negative 20x. 8x times 6 is 48x. And negative 6 times 4 is negative 24. Now we can see that the answer to the area is length times width, which in this case was 8x minus 4 times 5x plus 6, which we've just computed to see is 40x squared plus 28x minus 24 when I combine these terms. Let's do an example of probability. So in this situation, assume that half the population of the US can bend their thumbs backwards. That's like this. I can do it. I can also go this way, but it's bending the thumb backwards. And half of them can roll their tongues. I can't do that. I'm not going to try. Also assume that these genes are independent. In other words, having one gene does not affect whether or not you have the other. So you're not more likely to be able to roll your tongue since you can do the thumb thing. Also, they're randomly distributed throughout the population. So assuming these things, we can set up a area model. So notice it has roll tongue on the left, which is half and half. Half people can, half people can't. And bend the thumb on the top, bend their thumb on the top, which is half people can, half people can't. To find the probability of any of these things, we just multiply just like with the area model. So 1/2 times 1/2 is 1/4. And each one of these is actually 1/2 times 1/2. So we've got 1/4, 1/4, 1/4, 1/4. And combining like terms, I can see that the area of this is 1. So it says, what is the probability that a random person has both special traits? So the fact that they can roll their tongue and bend their thumb, we can see here's yes and here's yes. And those coincide here, which is 1/4 of the population, which in probability we generally write it as a percent. So 1/4, which is 25% of the people. Let's do another one. With the same kind of idea, the next one says, though, what's the chances a random person has one of these traits? So let me put my 1/4 back in here. And the fact that they have one of these traits, let's highlight which ones that happens in. So has only one, it should say. So this person has 2, so not them. This person just can bend their thumb. And this person just can roll their tongue, and this person can do neither. So 1/4 plus 1/4 in this case is 1/2, or 50% of people. Let's do a different situation. The last table assumes that half the population can bend their thumbs, but in reality only about 1/4 of them can, and the other 3/4 cannot. It also turns out that a lot more of the population can roll their tongues. I am not one of them. About 70%. How is this table going to be adjusted to represent these percentages? So here's my idea, is bend their thumb I can split up instead of being half and half to 1/4 and 3/4. And notice it's kind of sectioned out like that. Like if I split it into fourths, I only had 1/4 for yes. Roll their tongue, it's 7 out of 10. So this is going to be ugly. But I'm going to try to split this into 10 sections. I'm going to do half of them and I'm going to make these into 5s. 1, 2, 3, wait, 1, 2, 3, 4. There we go. 1, 2, 3, 4, 5. I think I did it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so roll their tongue is 3 out of 10. So these 3, okay, let me erase some lines now. Do you see where I'm going with this, I hope? So let's say these 3 represent the people who cannot. So 3 out of 10, no. 7 out of 10, yes. So now we've got our boxes. And if we were going to do the same kind of thing, whoops, sorry, and see if we can find the probability that they can do both. That would be the yes, yes. So that would be this section right here. Let me go to a different color. It's getting a little bit much. I'll go blue. Yes, yes would be here, which is represented by 1/4 and 7/10. So if I multiply those, I've got 7 over 40, which as a percent is 17.5%. So that is more accurate. It's about 17.5% of people can do both, as opposed to what we said earlier, which is 25%. Let's do a different situation. This one says, assume you can only receive blood from someone who is the same blood type as you. I know that's not technically the case, and there's lots of blood, and some people can give to everybody, and some people can't give to anybody, and so on and so forth. But just assume for this situation that there's types OA, B, and AB, and you can only receive blood from the person who has the exact same type as you. What are the chances two people will have the same blood type? In the following, the U.S. has these percentages. So let's see if we can set. All right, let's see what we can do here. So let's make this be person number 1 and this be person number 2. Person number 1 could have type O, which is 45%. Person A or number 1 could have type A at 40%, B at 11%, or AB 4%. Same thing for person 2. I'm going to put the same numbers on the top here. So let's see. We know with area model, we just multiply each section. So I'm going to do that. Let me pull up a calculator on the screen that I can keep up. So let's do it. 0.45 times 0.45 is 20.25. I'm just going to, in the case to make it simple for us, I'm going to round to the nearest percent. So this one would be 20%. So we're going to cut off the edges a little bit here just to make it nice. 0.45 times 0.40 is 18%. 45 and 11. So 0.45 times 0.11 is 5% approximately. 4% times 45%, 0.45 times 0.04 is 0.018. So that's approximately 2%. Let's do the same thing for the next row. 0.40 times 0.45 is 18%. I'm going to just go ahead and fast forward and do the rest here. All right, I filled in our table. Again, notice that we were just rounding to the nearest percent here. So some of these both say 2% when really they rounded up or down to that amount. And this one over here in the corner rounded to 0%. It was actually less than 1%. It was less than 0%. It was like 0.016%. But anyway, so here's our table. And let's see what we can do with it. Oops, sorry. So say we wanted to figure out if you had type A blood and you want to know what the chances are somebody else also has type A blood. So let's see, A blood, that's a 16% chance. Or O blood, it's a 20% chance. So the best situation you could have is if you had type O blood, because most of the population does. If you have type A, B blood, you're off for a long shot because not very many people do have that blood. Obviously, blood types are a little bit more in depth than that, and there's positives and negatives and stuff. But it's actually kind of interesting because there's a chart like this for those as well. My last example I just want to show you is the different types of sample spaces we've talked about so far. So you could write a list is one way, and that's shown here in the top. So that's one way is to write a list. This in the example is to flip 4 coins. In this situation, you could flip the coin 4 times and get heads 4 times in a row. You could also get tails, then 4 heads. I'm sorry, tails, then 3 heads, and so on. So these are all the options, and you can go through like that. Another way is to use the tree method, which is a situation that works well when there's equally distributed groups. So you're equally likely to choose hot dog, burger, or pizza, milk, water, soda, ice cream, and cake. So if everything's equally likely, this is your game plan for the tree model. Lastly, the area model is one where we set up a box, and it's really nice when things aren't actually equal because you can just section out things to show the probabilities of those sections. That's all I've got for today. I hope that you are feeling good on area model, and I will see you next time. Bye, guys.